All right, guys, we're going to work question number 2 of the E-Day, second E-Day free response that you showed me in class today. So if you want to fast forward to the end, you'll see all the work done, and you can compare your answers. But I'm going to walk through it step by step. This is a really interesting problem. We have this rotating box in which is a box and a spring. So as we tilt this up, eventually this is going to break free from friction and slide down and run into this spring. Now the first thing I want to do, because we're going to need this information later, is I want to make sure we can draw and understand the free body diagram for this box right here. Of course you've got gravity down, which is just mg, but we also then can break that into components. And to remind you, we call this force parallel, and it's mg sine theta, where theta is this angle theta, which is this angle theta here, the angle that we're tilting it before it breaks free. We also have this force vector here. It's the force perpendicular, and it's mg cosine theta. That results in a normal force that's equal to that. Normal force equals force perpendicular equals mg cosine theta. This is all review, so I'm not really going to take time to show you how we're figuring these out. You should know this. And then finally, there is a frictional force, and at first, it's static frictional force that acts that way. So we need that free body diagram of a box on an inclined plane before we can do A. I'm not going to read over the problem. I'm going to assume you've already done that. But basically, we're tilting this up until this box starts to slide. And then what the coefficient of static friction. So the idea is we want the net force down the plane. And that's going to be force parallel minus kinetic friction. And as we increase this, as we tilt it up and up and up, and it starts to want to slide, there's a point, that give point, where the box just starts to slide. And so the key is to understand that at this point, net force is 0, and force parallel equals kinetic friction force. Remember, static friction matches you pound for pound. So it's going to get bigger, bigger, and bigger, and bigger until it's just equal to the force parallel. All right? So now we just have to figure force parallel, which is mg sine theta, equals kinetic friction, which is mu static times normal force. Let's bring this up here. We need to plug in the normal force. So we're going to go mg sine of theta equals mu static, and normal force we said was mg cosine theta. The m's cancel, the g's cancel, and we get a very common equation. We've seen this before, where mu static equals sine theta over cosine theta, which quite simply is just tangent of theta. So what is the mu s coefficient of static friction? It's simply tangent of theta. Then we go to B, and it says find the total energy, the loss in total mechanical energy of the block spring system from the start, the moment the block starts to slide, to when it comes down, hits the spring, and comes down and rests. Now it's only resting for just a moment, but we want to know how much energy it's lost. We had some conversation today. Kudos to Preston Mantell as we were talking about how to figure this out. And I had oversimplified this problem. And so here's what you need to do. You need to say that there's mechanical energy initial, that's potential energy of this sitting up here, some height h above where it ends up. And we're going to lose energy along the way. Now what do we lose energy to? We lose it to friction, I suppose air resistance, a number of other things, although it's pretty much just friction. And that's going to equal our final mechanical energy. So we have initial, but we got to subtract the change in energy that we lose, and that equals final. And that is what we're looking for, and then we're looking for delta E. So delta E is equal to, if we want to get this by itself, it's going to be ME initial minus ME final. What is ME initial? Mechanical energy initial is mgh, that potential that the box has. And at the very end, the spring is compressed, but it's motionless, so all we have is 1/2 kx squared. All right? And that's delta E. But we don't want terms in terms of h. So I'm going to draw a picture of our box sliding down this ramp. And it's going to be, it starts out up here, a height h, and it's going to slide all the way down. And it's going to slide this total distance down, which is d plus x. All right? And hopefully you understand, the d is from here to when it hits the spring, and then it compresses the spring another distance x. So d plus x, this is theta, And we have this formula. Sine of theta is opposite, which is h over hypotenuse d plus x. So solving for h, we get d plus x times sine of theta. I just got h by itself there. Now we're going to put this over here in this formula. So the change in energy, or the energy loss, is mg, and h is d plus x sine of theta minus 1/2 kx squared. We can't really simplify for x anymore, so that will be the energy loss. It's in terms of the variables given. Mass, g, d, x were given, and so we're good to go there. And finally, they want to know the coefficient of kinetic friction. So the idea we're going to do here is we're going to do an energy conservation. Because at first it's static, it overcomes, but then when it's sliding, it's kinetic that's removing this delta energy that we just solved out. So what we're going to do is we're going to say mechanical energy initial equals mechanical energy final plus the work of friction. All right? So that's what we're going to do there. It's pretty much the delta E, but the idea is we have potential energy initial, mgh. The final energy it has is the spring, 1/2 kx squared. And what is the work done by friction? All right? It's going to be equal to the mu kinetic, all right, times the normal force, all right? And the normal force is what? Well, mu normal force times the distance. So that's what we get. So we're going to go mgh equals 1/2 kx squared plus mu k, the normal force, is mg cosine theta. I got that from up above, just to show you there's the normal force. And then the x is d plus x, because friction acts that whole way. All right? Now, I want to remind you that we then have, what is h? Well, it was mg d plus x times sine of theta equals 1/2 kx squared plus mu k mg, it's kind of long, cosine theta d plus x. And now we just have to get that variable by itself, which is not the easiest thing to do, but I think we can do it. So we're going to take this and subtract this and then divide through by all this. I'm going to try to fast forward to my answer, skip some algebra steps. So we're going to have this mg d plus x sine theta minus 1/2 kx squared all over, and we're going to divide through by this mg cosine theta d plus x. And so there is our final answer. There may be a way to simplify this as we zoom in on it here. There may be a way, maybe a way to simplify this answer. I don't know. I can't think of one right now. If you put this over this, everything cancels but the sine over cosine. So I suppose you could get tangent of theta, sine over cosine is tangent, and then minus kx squared over 2 mg cosine theta d plus x. So I suppose this is an equivalent answer, but that doesn't seem like it's any more simpler. And so that's what we've got. Let me back away so you can see all of these answers right there. Tangent of theta for A, this behemoth for B, and then C comes down to there. If you have questions about this, bring them to me, but that should be the answer. Thanks for tuning in, guys.